Hello everyone, welcome to the course on Electrical and Electronics Engineering. Today we are going to start Unit 2 where we are going to learn about analog electronics and integrated circuits. In this session we are going to see how a PN junction diode is constructed, its working principle and its characteristics. Similarly, we see the same for Zener diode also. Before going to the construction of PN junction diode, we should know PN junction diode is made up of P-type semiconductor material and N-type semiconductor material. So we should know what are the P and N-type semiconductor and what is semiconductor first. So let's have an overview of semiconductor, then go to the construction. So depending on the conductivity, materials are classified into three categories. One is conductor, other one is insulator, then it's semiconductor. A conductor is a good conductor of electricity. Insulator is just opposite, it's a bad conductor of electricity. Whereas a semiconductor has its conductivity lying between these two extremes. So seeing the energy band diagram, we can see the valence band is completely filled with or partially filled with electrons, but conduction band is almost empty, and there is an energy gap between these two bands. So seeing the three different materials, if you see metal, how the conductivity is good here, because here the energy band, valence band and conduction band are overlapped. Whereas an insulator, why it is not conducting? Because there is a large band gap difference between the valence band and conduction band. Whereas when we go for a semiconductor, there is a little gap. Okay, comparatively a smaller electric field is required to push the electrons from these valence band to conduction band. Actually, at low temperatures, the valence band, we know that it is completely filled and the conduction band is completely empty. Semiconductor, virtually it behaves as an insulator at a low temperature. But even at room temperature, some of the electrons, what they do, they cross over go to the conduction band, giving rise to conductivity. As the temperature increases, number of electrons crossing to the conduction band increases, hence the electrical conductivity increases. So we can say semiconductor has negative temperature coefficient of resistance. That means as the temperature increases, resistance comes down. That means conductivity increases. Fine. Now we can see the classification of semiconductor. Actually, the PN junction, which is made of P-type and N-type semiconductor, it's not a pure one. Okay, we will see where it is how it is classified. There are two classification. One is intrinsic semiconductor, other one is extrinsic. Intrinsic means it's a pure semiconductor, whereas extrinsic means it's a impure semiconductor. Because of the poor conduction at room temperature, what we are going to do, we are going to take the pure semiconductor and we are going to add some impurities. As such, if you use, it will not be useful in electronic devices. So to increase the current conduction capability of intrinsic semiconductor, we are going for the addition of impurities. So the process of adding impurity is known as doping. So to the existing intrinsic semiconductor, we are going to add a small amount of impurity, so which makes it as a impure semiconductor or extrinsic semiconductor. Right, now let us see what is N-type, then P-type. The N-type semiconductor, where we are going to add a small amount of pentavalent impurities such as arsenic, antimony, or it can be phosphorus. We are going to add these impurities to the pure semiconductor, which can be either germanium or silicon crystal, to get the N-type semiconductor. These addition of pentavalent impurities, what it do? It will increase the number of electrons in the conduction band, so that the conductivity of N-type semiconductor get increased. So because of the doping only, the number of free electrons is going to exceed the number of holes in an N-type semiconductor. So electrons are going to be the majority carriers in N-type and holes are going to be the minority carriers. Whereas in P-type semiconductor, we are going to add a trivalent impurity such as aluminum or boron to the pure semiconductor, right? Because of it, the number of holes is going to be very much larger than the number of free electrons. So holes are the majority carriers and electrons are the minority carriers. Now let us understand how a PN junction is formed. So in a piece of semiconductor material, if we take either germanium or silicon, if one half is doped by p-type impurity and other half is doped by n-type impurity, a p junction is formed. So the plane dividing these two halves, there is a plane, right? That is called p-n junction. So n-type material, as we see, it has a high concentration of electrons, whereas p-type material has a high concentration of holes. So at this junction, what happens? These free electrons have the tendency to diffuse to the p side, and the holes have the tendency, because of its excess in nature, they try to diffuse and go to the n side. So this process is called diffusion. Diffusion has happened. Okay. As the free electrons cross this junction from this n type to p type, what happens? Since it is crossing, these n-type materials are now positively charged. Hence, a positive charge is built on the n-type because they are donating, right? These free electrons that because we know the current conduction is due to only the electrons, right? These free electrons that cross the junction, what it do? It uncover the negative acceptor ions. Okay, by filling in the holes, it will fill the holes. Okay, therefore net negative charge is established on the p side of the junction. The net negative charge on the p side, what it does, it prevents a further diffusion of electrons into the p. Okay, similarly the net positive charge on the n side, what it do, it will repel the holes that are crossing from this p to n type. So a barrier is set up near the junction which prevents the further movement of charge carriers. Okay, for the movement of this electrons and holes, a barrier is set up. This is called potential barrier or a junction barrier, and it's equal to 0.3 volt for germanium. It is very less, whereas for silicon it is little bit higher, 0.72 volt. The electrostatic field across the junction caused by the positively charged n-type region, what it does, it will drive the holes away from the junction. Similarly, the negatively charged p-type region, they will try to drive away the electrons from their junction. So now the junction is depleted to the mobile charge carriers. Mobile charge carriers are not available now. Okay, so it is called depletion layer. Now we will see how a PN junction, we saw the construction of PN junction diode, what is the operation behind. Now we are going to see how to make this PN junction work. Either it can be worked in a forward bias or a reverse bias. Forward bias means the positive terminal of the battery. If you connect a battery to this PN junction, the positive is connected to P type and the negative terminal is connected to N type, means this bias applied is known as forward bias. So under this condition, the applied positive potential, what it does, applied positive potential, it will repel the holes in the p type. Already we are applying a positive here, majority are holes. It will repel the holes, so that holes, what it will do, it will try to repel, so it goes to the junction. Similarly, the applied negative potential repels the electrons in the n type to move towards the junction. Eventually what happens, when the applied potential, the battery biasing, if it is more than the internal barrier potential, the depletion region as well as the internal barrier potential both get disappeared. Okay, when the forward bias, applied forward bias is greater than the potential barrier, the barrier completely disappears, and hence what happens, the holes, okay, cross the junction from this p type and move there. Similarly, electrons cross the n type to the opposite, so there will be a large flow of current in this circuit. So as we can see, when the forward biasing is increased after the crossing the potential barrier of the germanium 0.3 volt, the current conduction is increased. Similarly, after crossing the silicon 0.72 that potential barrier, we call it as cut-in voltage, this forward current increases. So let us see what happens in reverse bias condition when the negative terminal of the battery is connected to P type and the positive terminal of the battery is connected to N type of your PN junction. The bias applied is known as reverse bias. Under this reverse bias condition, what happens? The holes which form the majority carriers in P side, what you will try to do, the holes are getting attracted towards the negative terminal of the battery. Similarly, electrons which are the majority carriers, they get attracted towards the uh, positive terminal of the battery. So what happens? The width of the depletion region, which is depleted of the mobile charges. Now these are the free electrons. Okay, and these free electrons are getting depleted. So the width of the depletion region increases. Thus, the electric field produced by the applied reverse bias, what it will be? It will be the same direction of electric field of the potential barrier. Both are in same direction. So the electric potential barrier is increased, which is going to prevent the further flow of majority carriers in both the directions. So theoretically no current flow in the external circuit, but practically there will be a small current in the order of microampere. Okay, from nanoampere to microampere, small current flows under the reverse bias. As we increase the reverse bias more, for the large applied reverse bias, the free electrons, okay, the free electrons from the N type move to the positive terminal of the battery. What it will do, these electrons get more energy and they move with high velocity, and these electrons will remove the valence electrons from the semiconductor atoms itself, and these newly liberated electrons, they again acquire sufficient energy to remove the other parent electrons. So these large number of free electrons are formed, so it is called avalanche of free electrons. So what these will do, these will lead to the breakdown of the junction now breaks. Now large reverse current flows. Okay, the reverse voltage at which the junction is going to break down is called breakdown voltage. So this is happening in the reverse bias. So this is a symbol of the PN junction diode, a triangle with a straight line. So this triangular portion is anode, positively charged, and the straight line is a cathode, or negatively charged. Practically, the diode look like the cylindrical shape, full of black, that is anode, and a slight silver lining at the end, which with the terminal denotes a cathode. Now let us learn about Zener diode. It is one of the special silicon PN junction diode, which is built with heavy doping. So these Zener diodes, they are primarily made from silicon semiconductor material. Okay, so it resembles the symbol of diode. Okay, but we have a AZ shaped cathode terminal here. Okay, anode terminal remains same, and this is the real time view of your Zener diode, where this black color coating represents the cathode. The small lining represents the cathode, and the rest is this terminal is the anode. So when the reverse voltage reaches the breakdown voltage in normal PN junction diode, what happens? The current through the junction and the power dissipated will be very high. Such operation is destructive and diode get damaged. So we can design a diode with adequate power dissipation capabilities to operate in a breakdown region. One such diode is known as Zener diode. So it is heavily doped, as I said earlier, it is heavily doped than the ordinary PN junction diode. So from the VA characteristics of Zener diode, we can find that Zener diode also has the same characteristics such that ordinary PN diode under the forward bias condition, whereas under reverse bias condition, breakdown of the junction occurs. So this breakdown voltage V is that it depends on the amount of doping. If the diode is heavily doped, depletion layer will be thin, and therefore the breakdown occurs at a lower reverse voltage, and further breakdown voltage also is sharp. Whereas a lightly doped diode have higher breakdown voltage. So we can control the breakdown voltage, or it can be selected with the amount of doping. So the sharp rising current under this breakdown conditions, they are due to two mechanisms. One is avalanche breakdown, other one is Zener breakdown. So we see one by one. As the applied reverse bias increases, the field across the junction increases correspondingly. So because of the field, the thermally generated carriers, while they are traversing the junction, they acquire large amount of kinetic energy from this field. Okay, so they occur the energy, and as a result the velocity of these carriers increases. So these electrons, they disturb the covalent bonds by colliding with immobile ions, and they will create the new electron hole pairs. These new carriers, again they will acquire sufficient energy from the field and collide with other immobile ions, thereby it will generate further electron hole pairs. This process is cumulative in nature, and hence we are able to generate avalanche of carriers within a short time. This mechanism of carrier generation is known as avalanche multiplication. This is due to the large applied reverse bias, and because of that the field get increases, right? These field only give the energy to the carriers. Okay, so this process result in a large amount of current at the same value of reverse bias. So when P and N regions are heavily doped, direct rupture of covalent breakage of covalent bonds take place because of the strong field at the junction. The new electron hole pairs so created, they will increase the reverse current. Okay, under the reverse bias PN diode, the increase in current, it takes place at the constant value of reverse bias. So typically below 6 volt for heavily doped diodes. So because of the result of heavy doping, the depletion region width becomes very small, and for the applied voltage of 6 volt or less, the field across the depletion region will be very high in the order of 10 power 7 volt per meter, and which makes this condition suitable for the Zener diode. For lightly doped diodes, Zener breakdown voltage becomes very high, and breakdown is predominantly happening by avalanche multiplication. Zener diode breakdown, it will occur only for lower breakdown voltage. Avalanche breakdown, as we saw, it occurs for higher breakdown voltage when we do a light doping. Okay, such diodes where both the breakdown occurs are called Zener diodes.